Hello again, everyone. I'm Sumner. I'm a graduate student in the Matter Lab in the Department of Chemistry at the University of Toronto. And today I'm going to be talking to you about Tequila, a software package that my group has been working on for about 8 months now. This software package is currently in its sort of live beta situation. So if you go to github.com/aspuru-guzik-group/tequila, you'll be able to find it. I will also screen share that page for those more interested. Now, since I'm going to be talking about quantum computing here, which I know is a field that many people might not have a lot of exposure to, might not know a lot about, I'm going to really quick show everyone a brief 2-ish, 3-ish minute presentation on what quantum computing is actually about so that we're all basically up to speed, so that we're all on the same page here. So I'm going to throw on some screen share and get to that now. All right. And let's throw this all up into full screen mode. I knew where this setting was 5 minutes ago. I should be able to find it again. And if not, oh well. So, quantum computing, a quick rundown. So, what do we mean when we talk about a quantum computer? What is a quantum computer? Well, it's quantum in the sense that it's an array of quantum systems. In general, those are two-level systems because we really have a sensible understanding of what those do. Those are easy to manufacture. We call a two-level system a qubit. It's the quantum analog of a bit. Using a quantum computer means controlling unitary evolution of a quantum state. For those not fresh on their math, a unitary is a matrix that is symmetric, or rather its conjugate is the same as its transpose. And when you multiply it by its conjugate transpose, you get the identity. So it's a specific kind of matrix multiplication. Physical quantum computers are things like tiny ions in a magnetic field in a laser trap, the polarization of individual photons in a circuit device, or even superconducting circuits chilled all the way down to single-digit millikelvin, where these macroscopic devices will begin to exhibit quantum behavior despite their micrometer to centimeter sizes. It's a computer in the sense that it implements exactly two operations. The first is that a unitary in the 2 to the n unitary group acting on vectors in the 2 to the n Hilbert space, no matter the unitary and no matter the state, is at most polynomial in n. Specifically, it should be no greater than n squared. There also needs to be some kind of quantum measurement. We refer to that as a POVM, a positive operator valued measure. And that should happen in constant time. That should take a quantum state that is on n qubits to a bit string of length n. This is collapsing the wave function, if we're all familiar with that term. How do these devices compare to classical computers? Well, a qubit stores information densely. That's one of its strengths. If you have n qubits, you would need 2 to the n classical bits to store the same state. And when n is anything modest, say 16, 32, 128, that's more classical bits than you're going to be able to find. They multiply matrices faster as well. That N squared scaling is a lot better than you're expecting. And entanglement on a quantum device is, in its own sense, though this requires a little more rigorous formalization, it is a computational resource in itself. These devices aren't magic, though. It's been proven that you can't copy a quantum state, an arbitrary quantum state, just given the state. There is no copy and paste on a quantum computer. When you measure a state, you change the state permanently. So there's this loss of information every time you try and actually get something out of the computer. Readout is a one-time event. And in a sort of more metatextual sense, these devices are sort of mind-boggling. It's hard to wrap an intuition around it. They don't work the way we're expecting them to, based on experiences with the rest of the macroscopic world. So that can influence our thinking about them in ways that may make them harder to use. The graphic I've included here, credit to the Wikipedia article on quantum complexity theory, shows where quantum theorists suspect BQP, which is the bounded time quantum polynomial complexity class. It's the quantum analog of P, how that relates to classical complexity. It includes all of P, some of NP, none of NP complete, and some of P space. That's a really weird overlap, but there's a lot of useful stuff that goes on outside of P and that isn't NP complete. So there's still a lot of power there. Just about the field a bit. I would identify sort of three major events if I had to pick three. There's, of course, been more. In 1984, Richard Feynman in a paper first theorized that quantum computers were what you would need to simulate quantum systems, which people were, and still are, having trouble with. It makes sense that you would need a device that could behave like a quantum system, or indeed was one, in order to actually replicate important quantum behavior. In 1994, Peter Shor published his factoring algorithm. This does in polynomial time what the best known classical computer requires exponential time to do. Famously, this means that the RSA encryption that your bank account uses is no longer safe the second someone gets their hands on a fully operating quantum computer. So, a motivating factor in sort of the further development of quantum computers and quantum algorithms was so that some evil mastermind with a quantum computer couldn't destroy the global economy. In 2019, sort of the most recent major milestone, scientists working at Google announced quantum supremacy for the first time. So that's the first time that a real quantum computer on a specific and well-defined task did better than any supercomputer could by orders of magnitude. That's the first time a quantum computer really, in a physical test case, proved its worth, so to speak. But I need to tell you a little bit about the state of the field to tell you about what it is I'm trying to do in this field. So we're entering what's been called the noisy intermediate scale quantum era. NISQ is what it's usually called in the quantum community. Here, the devices we have between tens and hundreds of qubits. They're noisy. You need to, if you're going to do anything useful, you need to use algorithms that are in some way resistant to noise, to random errors that we can't control, and you need them to be able to run fast. You can't get a deep circuit that has, thousands, hundreds of thousands of operations. That's not going to fly. Hundreds to 1,000 is where we're looking at. Now, the kind of algorithms that work well in the NISQ era are called VQAs, variational quantum algorithms. They're a hybrid class of algorithms in which some parameterized quantum operations are optimized by a classical optimizer. So there's sort of this three-way loop between the quantum device running a quantum circuit. That's how quantum scientists refer to these unitary matrix transforms that operate on quantum states. We have some measurement apparatus to send data back to a classical computer running a classical optimizer. And then we iteratively improve the performance of whatever task we've defined and have encoded into the quantum program. This leverages sort of the best of both worlds to the best we can. And there's a lot of theory and even some evidence suggesting that these are much more noise resistant than the strictly deterministic, unparameterized quantum algorithms that sort of first laid the groundwork of the field. Two kinds of algorithm that are really important, maybe the most important VQAs, are the VQE, originally pioneered by my research group back in 2010 or so. That's the variational quantum eigensolver. Given some Hamiltonian H and some parameterized unitary U of theta, your goal is to minimize the expectation value of that Hamiltonian acting on the state created by the unitary. Ansatz choices are critical here. They need to relate to the Hamiltonian in some way or you're not going to have any luck. And the real varying thing in this family of algorithms is what kind of classical parameter optimizer you use, what kind of unitary you're using, how you transform the Hamiltonian, and so on. There's also the quantum approximate optimization algorithm due to Edward Farhian et al. And this is a little bit different. It has a really well-defined ansatz. And here you've got a Hamiltonian where you've somehow encoded the right answer into the Hamiltonian. And here you're actually maximizing. A little bit of a difference in the way people think about these algorithms. So the software I've developed, Tequila. Tequila is an extensible quantum informatics and learning architecture. It's a recursive algorithm like GNU. Is focused mainly on these VQAs, especially on the VQE, and especially targeting chemical applications. Quantum chemistry is one of the leading applications of quantum computing in the current age. So without much further ado, I'm going to run through the actual usage of this software package. You should see now the GitHub for Tequila. Link up here in the top. That's https github.com/aspuru-guzik-group/tequila, like the alcohol.
Your screen is not visible.
The screen is not visible. Oh, wonderful.
Just share again.
Let's get that working. New share. Okay. Am I good now?
Yes.
Wonderful. Sorry about that, all you viewers at home. So the point of Tequila and the real design philosophy here is that we wanted to create a package that sort of worked the way quantum scientists think. A lot of the time we talk about these ridiculous operators that are easy to write down, exponentials of some infinitely long Hermitian matrix, talking about gates in terms of generators, talking about optimizing strangely transformed expectation values in unitaries. And we wanted to make that easy. Here's a little graphic with example code from Tequila showing how quickly you could write up and optimize a sort of bizarre exponential to the square objective. I'm going to dive right into some usage tutorials for Tequila real quick, though. So we're going to restart and run a bit. So basic usage of Tequila, it's a Python package. It interfaces a large number of other packages. Your favorite quantum simulators like Cirq and Qiskit, respectively packages affiliated with Google and IBM, are all available here. So just import Tequila as TQ and see what simulators we have. So we've got installed on my machine Culox, a very powerful simulator, very fast, Qiskit, Cirq, PyQuil, and a built-in symbolic simulator with a number of abilities, wave function sampling, regular sampling, noisy simulation in some cases, and this little subheading tells you what's installed. It's easy to create circuits, circuits again being the quantum analog of a program. You just use the Tequila gates module, and it has all the commonly defined gates you might look for, Hadamard, CNOT, whatever suits your fancy. So let's see what that circuit looks like. When you print it out, we just get a list of the gates, the qubits they act on, what controls them. So we've got a 2-qubit circuit here. We can draw the circuit out using Cirq's draw feature. And you just get what the circuit looks like. It's a Hadamard gate followed by the controlled NOT. That's as a quantum gate. But you can get a lot stranger than that. You can do double Hadamard. And you can also get some really longer circuits. This is all just playing around with various ways of initializing gates. So if you had a generalized rotation gate, which is just the exponential of a complex projector onto a state, Tequila can do that too, can compile it down to simpler versions. We can do easy simulation. So this somewhat complicated circuit acting on an all-zero state leads to one of the 4 magic basis states. This is the uniform superposition over all states. Who'd have thunk? We can simulate it with other. You can specify what backend you want to use. You could measure instead. So we see here when we run it, in this case with 10 samples, you always get the 0-0 state. You could do it considerably more. You get 6 times the 1-0, 4 times the 0-0. But we're really focused here on parametrized quantum circuits. So here we simulate just an RY gate. That's a specific quantum gate with just a string initialized variable. And all you need to do in Tequila to work with parameterized circuits is you pass down a dictionary of strings and numbers. And wherever you've thrown a variable, any hashable type into the circuit, we will handle that for you. So you don't have to do any kind of deep in the weeds wrangling with the simulation backend. But more importantly than that, we can transform this circuit. So we can exponentiate an angle inside, and you can say, okay, I'm going to feed you this number, but I want you to exponentiate it every time. And you just do that with the dot apply method. You can get really bizarre with your transformations. You could take the Gaussian of it, and you just apply your transformation as seen here. Run your circuit. Here we run it with the parameter A set to 1, and we get out, of course, simulatedly, a specific 1-qubit state. We could say have an angle that's a more bizarre hashable type. Any hashable type will work. So if you want to get really bizarre and you pass down the tuple 1, A, and it's a stupid example, that works too. We try to be as flexible in the code base as people might want to be. But the real focus here is on optimization. And for that, we have these really easy classes that sort of form the core of Tequila These are our objective and expectation value classes. Objective is just any transformation on any quantum or classical data, and an expectation value is what you actually measure on a quantum circuit, made up of some Hamiltonian and some unitary. We implement that directly as a class so that you don't have to figure out how to do it yourself. So we can use a simple unitary, Ry of some angle A. Our Hamiltonian will be the sigma x, and we can optimize that. Simulating it with the parameter a equals 1.0 gives us back a expectation value of 0.84147. This is a bounded expectation value since it's a single poly word, so it has to be between 1 and -1. But let's say that we cared about this and we wanted to optimize it. Or let's say we wanted to do it with some other circuit. We could build any Hermitian matrix we want and use it as a projector or as a Hamiltonian. Building it out of these poly words, the z, the y, the x in whatever fashion we want. And we can optimize over things that are more complex. You can compile the objectives and run them. And so when we compile an objective with this sort of bizarre Hamiltonian, x on all 4 qubits, y on 2, z on 0 and 1, tensor product with x on 2, and we optimize it, or sorry, we plot it over a number of values, we see that it's actually just this little oscillating thing. What if we want to run e squared plus 1, where e is our former? Well, we get a Gaussian 2. Or rather, we get 2 Gaussians. We have this, I wouldn't actually say Gaussians. We have this all above 0 oscillator with a different period. What if we want to shift it by e to the negative a squared, where a is the same variable we've been using in the circuit? You can do these sort of weird interactive transformations of quantum and classical data. What if you want to get absolutely crazy? What if you want to exponentiate the negative square of the expectation value itself? And then you wanted to add the exponentiation of the negative square of a variable and multiply that by an expectation value. We're totally agnostic to that. Here's what it looks like. It looks kind of like the back of a camel. One hump's a little bigger than the other. But other than that, everything works perfectly fine. However you want to build your objective, we can do it. You can take gradients of objectives. We interface the package JAX, the successor of AutoGrad, to let us automatically differentiate functions over quantum objectives so that you can optimize whatever you want agnostically of how the gradient is built if you're doing gradient-based compilation. So you see here, if we take the gradient of some objective, here we know that it's this sinusoidal function. We get back that its gradient has this over the variables, just like we'd expect for that sinusoidal function. And the second derivative is, as we are expecting for sinusoidal functions, the negative of the original. We have more examples even further. So this weird camel hump thing yields this as a first derivative and this somewhat bizarre second derivative. I'm a little low on time, so I'll dig real quick into interfacing more popular optimizer packages. Tequila, in addition to having plugins to all your favorite quantum simulation packages, also because it's targeted at VQA, has interfaces to popular classical optimization routines. Among them, SciPy, one of the most prolific optimization packages. We've built a setup that makes that easier for you to use. So let's say we have this Hamiltonian, sigma x plus some constant times sigma z minus sigma 0, or minus sigma z on a different qubit. Well, this Hamiltonian matrix is given here. Who knows what it really means? But that doesn't matter. You can optimize over it. So we'll build an ansatz. It's sort of hard to tell at this level what these unitary circuits are, but we have nice drawing features. So you can see that it's this series of gates, a few controls, several parameterized gates, and it's got 2 classical readouts. It is easy to simulate this. This circuit has 3 variables, A, B, and C, setting them all to 1/4. You get -6 times 10 to the who knows what. Squaring it and simulating it, you get an infinitesimal, as you'd expect for random variables. And you can optimize easily running the BFGS optimization, a gradient-based optimizer that's quite popular in the quantum community. You can minimize this, and we get that the best we can do is -2. Ballpark. We can get the parameters, final energy, and we've built in plotting features. So you can see there's this rapid convergence to the minimum we found. We can plot the angles over time, and we can plot the gradients over time as well. This final plot shows the angle C over time, but also its gradient from optimization step to optimization step. So I think I'm a little bit over time, but I'd like to point everyone who is interested back to the GitHub, or just Google a Spuru Guzik group /Tequila, and you should be able to find it. All right. Thank you very much for watching, and I suppose now I will turn it over for questions. As soon as I figure out how to get stop share to run.
So, stop. Thank you very much, Sumner, for this wonderful talk. So right now, I will ask some questions, and to the audience, if you have any questions, please do share them in the questions this chat box that we have on live.gitcommit.show. If you are not there, please go there and ask your questions. And also there is a clap button and to showcase your appreciation for the speaker and did you like this talk and or not. So now you can identify me as someone who is a quantum computing enthusiast. So I do not fully understand everything and what's going on there, but I am curious about those things. I have tried things such as CIRQ. I started trying that, but then I couldn't. So before actually I move on to the questions related to your talk, one question I have is specifically, how do I get started with quantum computing as a programmer who doesn't have the knowledge, all the knowledge that is needed to do these optimizations or move into this deep stuff. And on the same topic, I have this one specific question that how do I debug? I can write the code, I can use the library CIRQ, but how do I debug that? So that's my question.
All right. So if one has a strong enough programming background but needs to get deeper into the physics of what's going on, there's this one specific textbook that in the quantum science community is the first thing your supervisor puts on your desk on your first day of graduate school. And that is the textbook by Nielsen and Chong, by Michael Nielsen and Isaac Chuang. It's affectionately referred to as Mike and Ike. Every quantum scientist has that sitting above their desk. It's not the cheapest thing in the world, but I'd be surprised if you couldn't, with a little bit of finesse, find a PDF of it on the internet. It's excellent. It has most of what you need to get a working understanding of what's going on. It's significant enough of a textbook that it is mentioned on the Wikipedia timeline of quantum computing. So I would definitely recommend it. I think there's nothing I could really recommend more highly. if you want to really get a picture of what's going on, why does what's going on matter, what are we doing here? It's a great start. So actually developing. So the package you were talking about, Circ, was one that I sort of first cut my teeth on as well, so to speak. And actually moving with that to development, the difficulty of that is sort of what motivated building this package too, because, that code can get really in the weeds. It can get really idiopathic. There's hundreds of different quantum simulation codes out there. By my count, there's over 140. And so one problem that actually really affects the quantum community is nobody's really sharing their code. And even if they did, they wouldn't be able to tell what anyone else's code did unless they were familiar with the idiosyncrasies of umpteen different packages. So there's not really a straight answer on how to get developing seriously once you're familiar with that sort of coding apparatus, because the truth is it's sort of a Tower of Babel situation at the moment.
Got it. So, do you suggest the trial and error method? First, read about the book, read the book, and then try out the different simulators.
Yep.
Is that?
Yep. Find one that's your favorite and runs relatively fast on your computer, and just sort of tackle it. There are also various online courses that you can take. There's an edX course on quantum machine learning specifically, which is very good. It was originally taught by the now late Dr. Peter Vitek, who literally wrote the book on quantum machine learning. He unfortunately passed last year in a hiking accident in the Himalayas, but the course lives on, I believe should be free to access for all. And that is also a good way to get into some of the more specific cases and really see how things all come together.
Got it. Can you share more about your setup? How do you, when you code this, so the code that you showed us on Jupyter Notebook, when you code this, how do you, so you probably test it on simulator, or is there anything else involved, like testing it on live computer or anything else that's involved?
So we actually do have a plugin so that you can straight from Tequila interface the available quantum computers of the day. To my knowledge, there's only two companies that make actual quantum devices available to the public. That's the Rigetti Corporation and IBM Q. We have plugins for that. So anything that runs in a reasonable amount of time, we do try and make sure our code works well with those. Of course, time is expensive, so we try not to waste it. But mostly it's done by making sure everything works with the local simulator. It's at a point, we're at a point in the quantum community where you still want to know what a real quantum computer would do before you actually send your algorithm to it.
Got it. And are we able to make some programs which can add value to some of the stuff? Like what kind of calculations are we able to do? And can you share some benchmarks of those calculations so that people get to know the difference from normal computer and what we are doing here?
Right. So with currently existing computers, I'll be honest, not much yet. The noise remains a problem, though progress in recent years has been exponential progress. The size remains a problem, though again, exponential progress is being made, still to a goal that is some years away. It isn't the same as cold fusion, which has been 20 years away for 100 years. but it is still a more distant goal. But one application where it's quite clear that the quantum computer will be necessary is for simulating the energies of Hamiltonians for chemical systems. So you need exponentially good accuracy in those to be accurate, because the quantum energies of molecules, rates of chemical reactions depend exponentially on the differences between energies of various molecules. So a little error in the energy becomes a massive, absolutely massive difference in the reaction rate. And that's really important because we simulate these quantum molecular energies in a diverse array of fields. It's what you do for solar cell design, for drug discovery, for industrial catalysts. It's really the real money computationally in chemical and material science is doing this. And the quantum computer a fully working, large enough quantum computer can do in polynomial time in the number of electrons what a supercomputer takes exponential time to do, and it can do it better in that time. So in less time, it can do better. And when you get to a number of electrons that's pretty small overall, in terms of like active space, which is, how to generalize that, the electrons that matter, the ones that are participating in chemical bonds, when you're at 40, 60, 80 of those, still a pretty small molecule, those calculations are hard. Those calculations on a classical computer take hours. And in your average industrial discovery pipeline, you don't need to do 5. You don't need to do 10. You need to do 5 million. And so there's really the benchmark, the future benchmark, as it were, where quantum computers, I think, will really show their force.
How much time do you expect for that future?
It's hard to put proper bounds on it because it's hard to predict innovation. But I would be disappointed if it took more than 15. I'll put that as my stamp. Some people put it as short as 5. Some people are skeptical and put it at about 50. But I, for one, will be quite annoyed if I'm, losing my hair and still can't do that.
Amazing. So we have one person who is sharing that I was asking how I want to know the secret to your great enthusiasm. Your talk is so lively.
Secret to my enthusiasm. One thing, it's currently 1:45 in the morning here in sunny, warm Michigan, USA. So the secret to my enthusiasm right now is that my girlfriend bought a lot of expensive coffee and I've drank all of it.
Amazing. So right now we are running out of time, and I feel that there are so many questions that I need to ask, but we have to stop here. And can you to take this forward, we will share. Can you share this GitHub link you talked about, and also this book name and this EDX course that you coded, so that people can get started? We'll share that on our GitHub page, and we'll share with the audience. Other than that, second thing, can we? I think that will be the time when we are prepared for asking more questions. If in the audience they have any questions related to the talk, they can ask here, and probably we can take those questions via probably on GitHub discussions and then take it forward. Now, do you have any last message to share for the audience before we close this session?
I think not. Thank you.
Thank you, Sumner, for joining us.
Glad to be here.
See you. Bye-bye.